Okay, I have started recording.
Okay, now I'm starting. Okay.
Oh, okay.
Okay, welcome back to lecture 13 on Riemannian symmetric space. So last time we have seen this thing that pi 1 of SO3 is equal to Z2. Okay, we have proved this thing. And towards the end, after we finished proving this proposition, let G be a connected Lie group and H be a connected closed subgroup of G. So that pi 2 of G by S is equal to 0 is equal to pi 1 of G by H. Then pi 1 of G is equal to pi 1 of H. Last time I actually forgotten to this thing actually forgot to mention that G is connected in the hypothesis. So today actually I have corrected that. Okay. So the proposition is let G be a connected Lie group and H be a connected closed subgroup of G. So that pi 2 of G by H is equal to 0 is equal to pi 1 of G by H. Then pi 1 G is equal to pi 1 of H. Okay. Today we will apply this proposition. So now, okay, just wait a second. Okay, today we will apply this proposition. Okay, so some known facts. Actually, first so known facts. So this is really to take pi 1 of Sn. This is equal to Z if n is equal to 1 and 0 otherwise. Okay, this is known. And similarly, pi 2 of Sn is equal to Z if n is equal to 2. Okay, and 0 otherwise. So pi 2 of Sn is equal to Z if n is equal to 2 and 0 if it is otherwise. So that implies, so this implies pi 1 of Sn and pi 2 of Sn is equal to 0. Both pi 1 and pi 2 are 0 for n greater than or equal to 3. So this fact we will use. Okay. The first thing. So let us write that. So application of previous proposition. So first I really take I will apply that. I will take G is equal to SON and H is equal to SON minus 1. Okay. So we know that this SON mod SON minus 1 is equal to really SN minus 1. This is the okay. So now that and if for n greater than or equal to 4, this n minus 1 will be greater than or equal to 3. So that means pi 2 of I have told you that pi 2 of Sn and pi 1 of Sn is equal to 0 for n greater than or equal to 3. So pi 2 of SON mod SON minus 1 is equal to 0. This is equal to pi 1 of SON mod SON minus 1. So now, so for now I will apply that previous proposition for n greater than or equal to 4 because pi 2 pi 1 is 0. So by previous proposition, so pi 1 of, remember H is equal to SON minus 1. Pi 1 of SON minus 1 is equal to pi 1 of SON for n greater than or equal to 4. Now I will first put n is equal to 4. Then I will get pi 1 of SO3 is equal to pi 1 of SO4. Now I will get n is equal to 5. So I will get pi1 of SO4 is equal to pi1 of SO5, and I can continue in this way. So this will be same thing with pi1 of SON, n greater than equal to 3. Now I really know that pi1 of SO3 is equal to Z2. So that means pi1 of SON is equal to Z2 for n greater than equal to 3. Now for n is equal to 1, SO1 is equal to just singleton 1. So pi1 of SO1 is equal to identity 0. Or
this notation is Z mod 2Z, right? This Z2?
Z2 means Z mod 2Z.
Okay.
So Z2 I am writing. So pi1 of SO, we know that SO2 is nothing but homomorphic to S1. So pi1 of SO2 is Z. So n is equal to 2. Okay. So this is for SON. We do similar argument I will do for UN. So UN acts transitively on the unit sphere on Cn, and unit sphere on Cn is really homomorphic to, this is really homomorphic to S2n minus S2n-1. So this is homomorphism. In fact, so that means you apply that homogeneous. Okay, so you will get what? UN by UN minus 1 is homomorphic to S2n minus 1. Okay. This homomorphism. In fact, it is a diffeomorphism. If you know a little bit of law theory, you are using the theory of homogeneous space a little bit. You are fixing some point, and you are looking at a stabilizer of that point, and that is isomorphic to homomorphic to UN minus 1. You are using that. Okay. Now for n greater than equal to 2, this 2n minus 1, this is really greater than equal to 4, because, and therefore for n greater than equal to 2n minus 1, sorry, greater than equal to 3. Okay. So that means pi2 of UN mod UN minus 1 is equal to 0 is equal to pi1 of UN mod UN minus 1. Okay. So hence, now by applying previous proposition, we get this pi1 of UN minus 1 is equal to pi1 of UN for n greater than equal to 2. Now I put n is equal to 2, so I will get pi1 of U1 is equal to pi1 of U2. And similarly, I will put n is equal to 3. I will get pi1 of U2 is equal to pi1 of U3. So I can continue in this way. So this is actually pi1 of UN, and here I take n greater than equal to 1. Now what is U1? U1 is nothing but circle, e to the power I theta. So that theta belongs to R, and this is homomorphic to S1. So that means pi1 of U1 is equal to your Z. So since pi1 of U1 is equal to pi1 of U2, equal to pi1 of U3 is equal to pi1 of UN. So thus I will get this pi1 of UN is equal to Z for n greater than equal to 1. Okay. So C. Now C is for SUN. SUN also acts transitively on unit sphere on unit sphere of Cn, and this unit sphere of Cn is really homomorphic to S2n minus 1. Okay, so this is homomorphic. So this implies this SUN mod SUN minus 1. This is homomorphic to S2n minus 1. This homomorphism. So, and for n greater than or equal to 2, this 2n minus 1 is greater than or equal to 3. So that means pi 2 of SUN mod SUN minus 1. This is really pi 2 of S2n minus 1, and that is 0. Same thing as pi 1 of SUN mod SUN minus 1. Now, so now I apply that previous proposition. So hence pi 1 of SUN is equal to pi 1 of SUN minus 1. This is for n greater than or equal to 2. So that means pi 1 of SU1 is equal to pi 1 of SU2. And if I continue in that way, this is pi 1 of SU3. This is really pi 1 of SUN, and this is n greater than or equal to 2. N greater than or equal to 1. Because, okay. Now, SU1 is really your identity, singleton 1. So this implies pi 1 of SU1 is equal to your 0. So D is D. You know that SPN. I have shown that XPN acts transitively on the unit sphere of HN. Sphere of HN, and this HN is really the quatern n-dimensional quatern vector space, and this is really homeomorphic to S4n minus 1. So unit sphere of HN is homeomorphic to S4n minus 1, and we have also seen that SPN mod SPN minus 1. This is homeomorphic to S4n minus 1. Now this is for n greater than or equal to 2. This 4n minus 1 is greater than or equal to 3. So 4n minus 1 is greater than or equal to 3. Therefore, pi 2 of SPN mod SPN minus 1. This is equal to 0. This is equal to pi 1 of SPN mod SPN minus 1. Okay. So okay. So by applying that previous proposition, so this implies pi 1 of SPN SPN minus 1 is equal to pi 1 of SPN for n greater than or equal to 2 by previous proposition. Okay, so I put n is equal to 2, then I will get pi 1 of SP1 is equal to pi 1 of SP2. Similarly, pi 1 of SP3 and is equal to pi 1 of SPN, where n is greater than or equal to 1. So now what is SP? Okay, so let us. Okay, so what is SP1? SP1 is really Q belongs to H. So that norm of Q is equal to 1. And this is really a homeomorphic to S3. This is homeomorphism. So pi 1 of SP1 is equal to Z. Pi 1 of SP1 is trivial. So pi 1 of SP1 is really trivial because this implies from this relation pi 1 of SP1 are trivial. So all these pi 1 of SPN is equal to 0. for n greater than equal to 1. Okay, so this finishes the fundamental group of the so-called compact connected classical Lie group. So we want to really and by now we will use this to calculate fundamental group of so-called non-compact connected classical Lie group, and I will just give 2 examples only.
Mona,
Yes, sir.
another question. You are not using the word simple connectedness, but is this the reason why you are computing these fundamental groups, because you need to use Lee's third theorem?
Sir, I could not get your point, sir.
I'm saying you are showing certain groups are simply connected,
Yes.
and that is important for Lee's third theorem. Is this your motivation?
Lee's third theorem means which I am.
That Lie algebra homomorphisms comes as derivative of Lie group homomorphism.
Okay, yeah, that is the thing, and there are other things, sir. So if you look at this symmetric space, then you can prove that any symmetric space, any simply connected symmetric space, can be written as product of Euclidean type and compact type and non-compact type. This is important in many for many reasons. I'm doing it.
So if you give some motivation, that would actually help everyone.
Yeah. That is also as you said, that is also an important thing. But this is a very natural question to ask. Therefore, I am covering actually. Means just for completeness, and also as you said that you need simply connectedness for various reasons. Will I proceed, sir? Sir, will I proceed?
Yes, please.
Yeah. So fundamental and compact connected. I will just give 2 examples, and rest of the things you can really see. Examples A. So I will take let G is equal to this, suppose SUP comma Q. P is greater than equal to 1, Q is for this okay, we know that bipolar decomposition pi 1 of SUP comma Q is equal to pi 1 of SUP comma Q intersection U P plus Q. And this is really, we have calculated this thing. This is really pi 1 of SUP cross SUQ. So this is really pi 1 of SUP cross pi 1 of SUQ. No, sorry. Actually, we have calculated this thing as this is cross S1. SUP comma Q intersection UP plus Q is equal to homomorphic to SUP cross SUQ cross S1. So this is really pi 1 of S1 so this is first one is your 0, and second one is 0, and third one is really Z. Okay. So you will get that is Z. Okay, so now the second thing is really you take, let us say G is equal to, okay, so let us use a press space. So G is equal to SO naught P comma Q. So pi 1 of SO naught P comma Q is equal to pi 1 of SO naught P comma Q intersection U P plus Q, and this is P greater than or equal to 1 Q. So this is really pi 1 of, this is SOP cross SOQ. We have seen that SO naught P comma Q intersection UP plus Q is equal to SOP homeomorphic to SOP cross SOQ. So this is really the same thing as pi 1 of SOP plus pi 1 of SOQ. Okay, in this case we will get a table something like this. Okay, so P is equal to 1, P is equal to 2, and P greater than or equal to 3. Similarly, Q is equal to 1, Q is equal to 2, and Q greater than or equal to 3. So pi 1 of SO naught P comma Q. So actually, what is pi 1 of? Yeah, look at this. Pi 1 of SN is equal to 0 if n is equal to 1, n is equal to 2, this is Z, and n greater than or equal to 3, this is Z2. Okay, so you will use that thing. So if P is equal to 1, Q is equal to 1, this will get 0. P is equal to 2, Q is equal to 1, then this will, you will get, this is Z, and P greater than or equal to 3, Q is equal to 1, this will you get Z2. P is equal to 1, Q is equal to 2, this will you will get Z. P is equal to 2 and Q is equal to 2, this will you get Z cross Z, and P Q is equal to 2, P is greater than or equal to 3, you'll get Z cross Z2, and this is really Z2, and Q greater than or equal to 3, P is equal to 2, this will be get Z cross Z2, and final thing you will get Z2 cross Z2. Okay, so this is the fundamental group of pi 1 SO naught P comma Q. Similarly, you can really calculate the fundamental group of other groups. Okay, so what I have done, I have maintained a table, and you just verify that those things after in the okay, you just verify those things after the leg class. This pi 1 of GL plus NR is equal to 0, n is equal to 1, Z, n is equal to 2, Z2, n greater than or equal to 3. Similarly, pi 1 of SLNR, this is equal to 0 for n is equal to 1, and Z for n is equal to 2, and Z2 is if n greater than or equal to 3. So in particular, this SLNR is not simply connected if for n greater than or equal to 2. Okay. So similarly, I have just given I have calculated all the fundamental groups here. We just verified. So now this finishes everything about classical group, but I have to just discuss one question. So this is a simple question, but so given example of Lie group, which is not a matrix Lie group. So okay, so matrix Lie group. So answer or example. First, you take this SLNR universal cover of SLNR for n greater than or equal to 2. It is known that if G is a Lie group, that its universal cover is also a Lie group. So this is the universal cover of SLNR. Now, since n greater than or equal to SLNR is not simply connected, this is really a okay. the SLNR tilde is not equal to SLNR. So probably this is the right place to prove this thing. But since you do not know a little bit of but it requires some Lie theory, therefore I am not doing it. So I am just saying for, and in fact any non-trivial cover of SL2R is also not a Lie group, not a matrix Lie group. Trivial connected, I should add. Non-trivial connected. Third,
Is there any simple way to write this group?
yeah, actually I do not know. There are some explicit way to write this thing, SL2R tilde, but I do not. At present, I don't remember those things. Okay, I have seen that one size. Okay, and these are not only just these are not these. Actually, there are other examples also. For instance, you take this H is equal to say Heisenberg group. This is 1 AB 0 C 001 A comma B comma C belongs to R. This is a matrix Lie group. H is a matrix Lie group. Now you take this N, where this is 1 0 N 0 1 0 N belongs to Z. Then this N is a closed normal subgroup of H. Yeah, this is how you can take it as an exercise.
Actually, in the center.
Yes, sir. Yeah.
Actually, the center.
Yeah. And therefore, since N is a closed normal subgroup, you can take this thing. It is in the center actually. So this H by N is a actually is a Lie group actually. You can say that, and this H by N is not a matrix Lie group. So there are many examples, but these are some standard examples. Okay, so this finishes about something like. Hopefully, I will do this example if they are. I will after
Just go back. Just go back. Yeah. So it is a Lie group, but it is not a matrix Lie group.
which this H is a matrix Lie group.
Yeah. But H mod N is not a matrix.
Not
Lie
a, yeah. So this finishes about the thing. Let us move to some other things. Okay. Yes. Yes.
The reason question by N is not a group, is there any quick reason, quick argument involved or rigorous calculation there? Means why is not a matrix group?
Actually, you look at Hall. Actually, it is not difficult to not difficult to see it, and I could have done it, but the thing is, I do not remember at this moment because, and this is also not difficult. First example, after you calculate this fundamental group, then this is not at all difficult. Okay, so maybe after some time I can do it, or I can just I can look at my notes and I will make a photocopy of that and I will send to you if it is. This is not difficult. Actually, first example, you have to just
Regarding 3, you are basically saying that it is not a closed subgroup of GLMC.
Yes, sir.
Right?
Yes, sir. No, actually, sir. Yeah, I am close. I do not know. Actually, I cannot recall this at this moment.
Thank you.
Yeah, it is not closed subgroup of GLMC. Okay, this is what is the definition of matrix Lie group, right? Okay, this is the thing actually. Let us see after some time, maybe we will do this thing. Okay, so let us move towards something today. So you know this, there is something called polarization identity. So for this inner product space, and this is really inner product space, you take VW. So this something happens like 1 by 4 k is equal to 0 to 3 I to the power k. This is v to the power I to the power k w norm square. Okay, this is called polarization identity for this inner product space. Okay, now similarly, we have a polarization identity for bilinear form.
So what is this I? This is the complex I?
Yes, yes. Yeah, this is complex I. So for Hermitian, let H be a Hermitian form. On a finite dimension, finite dimensional vector space over C. Okay. Assume S is non-degenerate. Such a non-degenerate is not required, but generate. So I define this something called QH of V. QH of V is equal to, see, this is H of VB. So this is called quadratic form associated to H. Associated to H. Okay. So now I have a polarization identity for Hermitian form. So you can sort of guess what will be the thing. So polarization identity. Actually, this will be H of VW. This will be 1 by 4. K is equal to 0 to 3. I to the power K QH of V plus I to the power K W. VW belongs to V. See, the thing is, inner product is a Hermitian form, and which is positive definite. And for proving this identity, the star, we do not need that positive definites of this inner product. So for that reason, this is trivial. This is actually, we don't have to really prove this thing. Okay. So now, I look at this automorphism group of H. So this is really T belongs to endomorphism of V, so that this is H of TW is equal to H of VW for all VW belongs to V. So this is my, and because of this polarization identity, so this will be same thing as T belongs to endomorphism of V, so that QH of TV is equal to QH of V for all V belongs to V. Okay, this is because of polarization identity. It says that something is really preserves the Hermitian form if and only it preserves the quadratic form. Okay, so now the thing is, okay, so for bilinear form, I have an analog. Bilinear form case. Okay. So let B be a non-degenerate symmetric. The symmetric is important here. Otherwise, this quadratic form will be 0. Symmetric bilinear form and a finite dimensional vector space over field K. Here K is equal to either R or C. So similarly define this QB P is equal to B of VB. Okay, this is as usual. This is also called quadratic form associated to B. Now the thing is, I have a polarization identity here, and to write this polarization identity is very easy, because you know that in one-dimensional case, this is the simplest quadratic form, ZW. So ZW, you have this thing 1 by 4 Z plus W square minus Z minus W square, and this is really 1 by 2 Z plus W square minus Z square minus W square. This is 1 by 2 Z minus W square. Oh, sorry. By 2 Z square plus W square minus Z minus W square, and from this you can write what is the polarization identity. Thus B of BW, this will be 1 by 4 QB of B plus W minus QB of B minus W. This is equal to half QB of B plus W minus QB of B minus QB of W. This is half QB of B plus QB of W minus QB of B minus W. So this is my polarization identity, and because of this polarization identity, the automorphism of P is equal to T belongs to endomorphism of B over K B2 TB is equal to B of UV for all UV belongs to B. So this is same thing as T belongs to endomorphism of B over K. QB TU is equal to QBU for all U belongs to B. Okay, so this is the important thing, and we will. This is useful in this will be used in certain cases. So let us move to a new topic. Okay. Okay. I also recall one thing. Recall that this O n comma 1 has 4 components. So first is this O plus plus n comma 1. If you, this is A star B belongs to O n 1. So the determinant of A is really greater than or equal to 1. B is greater than or equal to 1. O plus minus n1 A star B, this belongs to O n1. So the determinant of A is really greater than or equal to 1, and B is less than or equal to minus 1. So this O minus plus n1 is so the determinant of A is less than or equal to minus 1, and B is greater than or equal to 1, and O minus minus n1 So the determinant of A is less than equal to -1 and B is less than equal to -1. So we have seen this, and we have seen that this SON comma 1 is really O plus plus N1, a distant union O this minus minus N1, and also we have seen that SO naught N comma 1 is equal to O plus plus N1. Okay, so now we will move to something interesting geometric space, something called n-dimensional hyperbolic spaces. N-dimensional hyperbolic space, and this is denoted by HN. Okay, so we want to really cover this thing.
You are including real complex everything in HN.
I will do sir one, and then actually after symmetric space, I will cover this thing. Then I will talk about this complex and quaternary. First, I will
So
do
this
this
is
real case. So okay, real hyperbolic space I should write. So n-dimensional real hyperbolic space. Okay. So let x y belongs to Rn plus 1. Okay, so this is really, we have this bilinear form. I will write this bilinear form like this: x1 y1 plus x2 y2 plus xn yn minus xn plus 1 yn plus 1. So we know that this is the bilinear form which defines the group On comma 1. So n comma 1 resolves this thing. Okay, and this is also symmetric bilinear form. So quadratic form, what will be the quadratic form? This will be x1 square plus x2 square plus xn square minus xn plus 1 square. Okay, I take this first, this set S. This is x belongs to Rn plus 1. So that qx is equal to -1. We will draw the picture later. First, I wanted to. Actually, this S is actually a smooth manifold. Since actually I will not prove, I will give this, since -1 is a regular value of the function q. Actually, value of q, this S will be a smooth manifold. Smooth, actually manifold. In fact, it is a submanifold of embedded submanifold of Rn. So S is a smooth manifold of dimension n. Okay. So you can look at the book Kumulation. See Kumulation. Okay, so this is a manifold. Now, so check that this En plus 1, which is 1, 0, 0, 0, and 1, this belongs to S. Okay, and minus of En plus 1 also belongs to S. This is because this is very trivial, okay, to see that. Now let x belongs to S. So that means this implies this qx is equal to -1. So this implies, okay, so qx is equal to -1. This implies x1 square plus x2 square plus xn square minus xn plus 1 square. This will be -1. So this will be x1 square plus x2 square plus xn square plus 1. This is really will be xn plus 1 square. So since x1, x2, xn are real, this implies xn plus 1 square is equal to greater than equal to 1. So that implies that xn plus 1 is either greater than equal to 1 or xn plus 1 is less than equal to minus 1. So I took this thing hn. I will define this xn. Hn is equal to x belongs to s. So that xn plus 1 is greater than 0. Because xn plus 1 is either 1 greater than equal to 1 or xn plus 1 is less than equal to minus 1. So this is same thing as x belongs to s. So that xn plus 1 is greater than equal to 1.
So what was your S?
S is the x belongs to Rn plus 1. So that qx is equal to minus 1.
Minus 1.
Just minus 1. It will be okay. I will draw a picture of this s. So similarly hn tilde, this x belongs to s, so that xn plus 1 is less than 0. So x belongs to s, so that xn plus 1 is less than equal to 1, minus 1. So now it as hn is a really is an open subset of s. So that means this implies hn is also a smooth manifold of dimension n. Similarly, this hn tilde is also a smooth manifold of dimension n. Okay, so now the thing is this en plus 1 has last coordinate greater than equal to 1. So en plus 1 is belongs to hn, and this minus of en plus 1, this belongs to hn tilde. Okay. Now, okay, so we want to really draw the picture of this so-called s. Okay. Now, so let okay, I will write like this. Write x is equal to say x prime and xn plus 1. What is x prime? X prime is the first n coordinate, x1, x2, xn. Now qx is equal to minus 1. This is same thing as x1 square plus x2 square plus xn square is equal to minus xn plus 1 square. This is equal to minus 1, right? Now this will be same thing as x prime square, norm of x prime square minus xn plus 1 square is equal to minus 1. Now if you are really, if you know the concept of something called surface of revolution, it is not easy, not difficult to see that this will look like something. So this will be something. Okay, let me draw this, then you will really. Okay, so this. So just wait, huh? Okay, so now you will have to just rotate this. So, okay, so this is really xn plus 1 direction. This is my, this point is my en plus 1, and this is my minus of en plus 1, and okay, so and this plane which I am xn actually which this line which I am means I am coloring in the red line, this represents the plane of x prime also. So actually this will look like some thing like two sheets of hyperboloid. Okay, and upper half thing is upper plane is this thing is your HN, and lower is your HN tilde. Okay, so now from figure, okay, from figure you can see that this HN tilde HN is looks like a connected set. Okay, and it will be connected. We'll prove it. But the thing is, this is not a proof. Okay, so you should just, you can believe that now that HN will be connected from the figure. Okay. So is it clear, Tapendu?
Yes,
Tapendu is
Madhav.
yes. So now the thing is, see, the thing is Q or T preserves this quadratic form because n comma 1 matrices this preserves the quadratic form. So this implies it is easy to show, see that. So on comma 1 preserves S as preserves S, thus defines a group action on X. Group action on S. Okay, what we will see first, this is, we'll see claim, we will see that this is SO naught n comma 1 mod SON. This is really, this is homeomorphic to HN, and if you little bit, this is in fact diffeomorphic to European. Diffeomorphism. Okay, so but I will really, now I will at least prove this is homeomorphism. Okay, so let us do that first. So let P is equal to say P1, P2 up to Pn plus 1. This belongs to Hn. Okay, so since P belongs to S, and by definition of Hn, this last coordinate is greater than or equal to 1. So this implies that Pn plus 1 is really greater than or equal to 1. Okay. Now I take this. Okay. So let W is equal to P perp. P perp, this perpendicular is with respect to bilinear form. With respect to this. Okay. So this is by definition, this is B belongs to Rn plus 1. So that PV is equal to 0. Okay. So I have to really prove that this is actually dimension of W is n first. So claim. So W is a n-dimensional vector subspace of Rn plus 1. Okay. So vector space it is clear. So proof, check that W is a subspace of Rn plus 1. This is clear from this bilinearity property. Now let P belongs to W, and say V is equal to your V1, V2, Vn plus 1. So that means as V belongs to W, so that will imply this P1 V1 plus P2 V2 plus Pn Vn minus Pn plus 1 Vn plus 1. This will be 0. So that will give you Pn plus 1 Vn plus 1 is equal to P1 V1 plus P2 V2 plus Pn Vn. Now P1 plus 1 is greater than or equal to 1, so I can divide this thing. P1 V1 plus P2 V2 plus Pn Vn by Pn plus 1. So from there actually you see that if you fix these coordinates of v1, v2, vn, then vn plus 1 is fixed. So that precisely says that w is of dimension of Rn plus 1. W is of dimension n. Okay, so precisely what I'm saying, precisely if you take, suppose you take v1 is 1 and everything is equal to 0. So this is 1 0 0 0 and last two coordinate will be v1 is equal to 1. So what I'm saying, this last coordinate will be p1 by pn plus 1. So similarly, w2 will be 0 1 0 0 0 p2 by pn plus 1, and this wn is equal to 0 0 0 1 and pn by pn plus 1 is a if this thing w1 w2 wn will be a basis for w. This is clear, but if you know this is bit about this bilinear form, then it is also clear from there. So remark, if w of u is a subspace of okay, remark also. Let P be a finite dimensional vector space for K equipped with a non-degenerate bilinear form B, then dimension of U plus dimension of U per is equal to, this is equal to dimension, this is true. So using this result, it is also, you can in one line you can conclude that dimension of W is n because of P has dimension 1 and the space has dimension n plus 1. Therefore, its complement has dimension n. So this is clear now. Now next thing is very important. So claim this bilinear form is positive definite on P, W is equal to P per. So in other words, so this will be this is an inner product on W. So this claim will be used to give a Riemannian structure on HN. Actually, if you know a little bit of product on this W. Okay, so proof is, so let V belongs to W. So this implies this P1 V1 plus P2 V2 plus Pn Vn minus Pn plus 1 Vn plus 1. This is equal to what? This will be 0. So I can write that like Pn plus 1 Vn plus 1 is equal to P1 V1 plus P2 V2 plus Pn Vn. So I take the modulus in the both sides. So and I really apply the Cauchy square inequality. So Cauchy square inequality, I'll get this P1 square plus P2 square up to Pn square over this is V1 square plus P2 square plus Pn square. Now I square it, so I will get P1 plus 1 square, Bn plus 1 square less than equal to P1 square plus P2 square plus Pn square and B1 square plus P2 square plus Pn square. Now, okay, so as P belongs to a chain, this means this implies P1 square plus P2 square plus Pn square is minus Pn plus 1 square. This is equal to minus 1, and therefore P. So this implies P1 square plus P2 square Pn square. This is equal to Pn plus 1 square minus 1. So I put that. So this will be Pn plus 1 square, Pn plus 1 square. So I will get that P first thing I will put Pn plus 1 square minus 1, B1 square plus B2 square plus Bn square. So I will open up this. I will expand that and I will get P1 square, B1 square plus B2 square plus Bn square minus of B1 square plus B2 square up to Bn square. Now look at this left hand thing. I will take this minus of B1, B2, Bn square to the left, and I will take whatever there in the left I will take to the right. So I will do that. So I will get B1 square plus B2 square plus Bn square. Okay, so I will take the common Pn plus 1 square. So this will be B1 square plus B2 square plus Bn square minus Bn plus 1 square. Okay. Now you look at this expression very carefully. This expression is nothing but this B. This is so I will get what B1 square plus B2 square plus Pn square by this Pn plus 1 square. I can divide by Pn plus 1 because it is non-zero. So BB. So this implies BB is greater than equal to 0 or any B belongs to W, which is nothing but P power. So okay, now call this one. Suppose BB is equal to 0, then if BB is equal to 0, then this implies B1 is equal to B2, this is equal to Bn is equal to 0 from 1. Okay, so this will be Bn is equal to 0, but okay, and now as Pn plus 1 is equal to P1 B1 plus P2 B2 plus Pn Bn, and B1 B2 Bn all are 0. This is 0. This implies Bn plus 1 is equal to 0, as Pn plus 1 is not equal to 0. So this implies so what I am getting? So I am getting B is equal to 0. This implies B is equal to 0. So this is an inner product on W. Okay, on P power P is equal to W. So now since this is in inner product on W, we can choose an orthonormal basis. Basis U1, U2, UN. This belongs to W with respect to this this bilinear form, because This bilinear form is really not product. So we set un plus 1 is equal to p. Okay. Now, so for 1 less than equal to I less than equal to n, this is thing is really good. So ui use this is equal to 0, right? Because of by construction. And okay, for 1 less than equal to I less than equal to n, this is thing is ui un plus 1. This is really ui p, and this is also 0. So now okay, un plus 1, this is really pp, and this is equal to minus. Now look at this condition. 1, say this, okay, so let us say this is a, this is b. So a comma b commas and c imply that the matrix T is equal to, if I take this matrix u1 u2 un plus 1, this is belongs to on1. This is the precisely the condition for which this matrix, if you look at T, this where columns of T is u1 u2 un plus 1, this belongs to n plus 1 because of this condition a comma b comma c. Okay. Now what is, so T of en plus 1, this is equal to un plus 1, this is equal to p, and we have seen that p since pn plus 1 is greater than equal to 1, this means n plus 1 comma n plus 1 entry of n plus 1 entry of T is greater than equal to 1. Okay. So that means T belongs to, by definition, this implies T belongs to O plus plus N1 disjoint union O minus plus N1. Okay, so now this has we have seen that this has determinant is equal to 1, and this is determinant is equal to minus 1. The determinant is equal to minus 1. So if necessary, by changing u1 to minus 1, we can assume determinant of T is equal to 1. So that means this implies that T belongs to O plus plus N1. So what I am getting, okay, so since T of En plus 1 is equal to P, and P is arbitrary, we get that O plus plus N1 of En plus 1 is equal to Hn. So now, so that means whole Hn will lie inside the orbit of En plus 1, Now I look at this O plus plus N1 Hn, and this is same thing as O plus plus N1 and O plus plus N1 En plus 1. So okay, I am replacing this Hn in place of Hn by this simply O plus plus N1 and En plus 1. So this is really O plus plus N1 and by since this is I am using this group action property, and this O plus plus N1 is a group. Okay, so what I am getting, so this implies O plus plus N1 Hn is equal to O plus plus N1 of En plus 1, and this is really your Hn. So okay, O plus plus N1 is Hn is equal to Hn. So O plus plus N1 acts transitively, and this is actually, this action is also smooth transitively on Hn. Okay, so now okay, we want to really let okay, so let f is equal to stabilizer of this En plus 1 inside this group O plus plus N1. Stabilizer of this En plus 1 inside this group. Okay, so now let T belongs to F. Okay. So this as T in En plus 1 is equal to really En plus 1, therefore T is of the form something like G1, G2, Gn, and last column is En plus 1. Okay. So now we have used this notation, the V1, actually if V is equal to say V1, V2, Vn plus 1, this notation I have used this Vu is equal to say upper thing up to first n thing, V1, V2, Vn, and Vl is equal to your Vn plus 1. I will use this notation because okay, I am sort of notation. So that for that reason I is T is equal to so G1U and G1L, G2U, and this is G2L, and GNU is equal to GNL, and this is 0, 1. Okay, so let A is of this matrix G1U, G2U, and GNU. Okay. So, and this A is a n cross n matrix. So since T is equal to say G1U, G1L, G2U, G2L, GNU, GNL, 0, 1, this belongs to O n comma 1, O plus plus n1. So that implies that so G I, this is En plus 1, this is equal to 0 or 1 less than equal to I less than equal to n. So if you calculate that, that will give you so GIL is equal to 0 or 1 less than equal to I less than equal to. You just expand this, you will get this. So now, so GIU inner product GJU for this will be actually, since GIL is equal to 0, G2L, GNL is equal to 0. So this will be This will be same thing. This is an Rn. Same thing as Gi, Gj, this bilinear form. Okay. So this is actually for 1 less than equal to I, j less than equal to n. So, but Gi, Gj is really delta Ij. So this means G1, okay, delta Ij. But this means G1u, G2u, Gnu. Okay, so these things G1, G2, Gnu, this forms a orthonormal basis of Rn. So this implies, and these are really columns of this A. This implies A belongs to On. So this implies I will take 10 minutes, probably more. Actually, I need to finish this thing actually. So let T. So this implies T is of the form. So T is of the form A 0 0 1. A belongs to On. Now as T belongs to O plus plus N1, that means this means the determinant of A is equal to really greater than equal to 1. So, and since A belongs to N, this determinant for A is equal to 1. So that means F is equal to this form A0 0 1, so that A belongs to SON. And this is really homeomorphic to SON. And this is actually we will not really distinguish between this group left hand side with SON. By SON, I will mean this thing. Okay. Actually, here n plus 1 n. Okay, so this is really thing what I am getting. So by theory of homogeneous space, I am getting we get this O plus plus N1 mod SON. This is really HN. This is actually homeomorphism. Actually, this is much more than homeomorphism. This is actually in a diffeomorphism. Because if you really, I have not told you, but this is actually diffeomorphism. So since this O plus plus N1 is connected, since O plus plus N1 is connected, this implies this HN is connected. Okay. Now, okay. Now this okay. So I approve this HN is connected, and this HN is equal to O plus plus N1 and SON. So, but O plus plus N1 is SO not N comma 1. So thus we get this SO not N comma 1 mod SON is really HN. Now I want to look at this O plus minus N1 and HN. So this is really what? Something like I2 tilde into O plus plus N1 and HN. Okay. Where this I2 tilde is equal to diagonal of something like 1 1 1. Last thing is minus 1. So this is really, but O plus plus N1 HN is equal to your HN. This is equal to I2 tilde into HN. Okay, so since it multiply this matrix I2 multiplies the last coordinate by minus 1, so it will be really HN tilde. Similarly, okay, so O minus plus N1HN is equal to something like I3 tilde into O plus plus N1 into HN, and where this I3 tilde is equal to diagonal of this is 1 1 minus 1, first one will be minus 1 and this is 1. So but I3 tilde and this is first one O plus plus N1 into HN is really this will be HN and I3 tilde of HN is again HN. Similarly, I will get we will get O minus minus N1 HN is equal to really HN tilde. Now look at this thing. If you look at SON1, this SON1 actually this is disjoint. Sorry, this will be disjoint union of this O plus plus N1 and O minus minus N1. But O minus minus N1 HN is HN tilde. So that means this implies SON comma 1 doesn't preserve HN. Okay. But what is preserving HN? This O minus plus SON1. So this will actually preserve HN. So let G is equal to O plus plus N1 disjoint union O minus plus N1. So check that G is a group and stabilizer of G in En plus 1. This is really A001. This is A belongs to On. And so this is homomorphic to On. So this is exercise I can give you. So I am getting this. Thus we get G mod On is really HN. We will show later that HN is a Riemannian manifold. And isometry group, I will define something. Isometry of HN is equal to G. So this gives an introduction to this HN, and this is a very important symmetric space. This will be later we will call this as symmetric space of non-compact type. So with this I would like to stop, and I will be happy to answer if there is any question.